Hey dudes, we're checking out 6.3. It's out of 16D in the text, inflection and shape. Really we can start with a concavity, which talks about is it facing up or facing down. It doesn't necessarily have to be a parabola. A function doesn't necessarily have to be a parabola. It could be something like a cubic, and in some spots it's concave down, and in other spots it's concave up. And in the point between is a point of inflection where it switches from one to the other. We can recognize concave up or concave down in limited domains because of how the slope is changing. So if you looked at an upside down parabola, an inverted parabola, the slope would be positive on one side, get less positive, go to zero, become negative, become more negative. Right? And you can see that the slope, instead of calling this f prime of x, maybe we could call it the slope of the tangent. You can see that the slope of the tangent is decreasing. It's positive here, it goes to zero, getting negative, so the entire time the slope of the tangent decreases. Therefore, it means the slope of the tangent's derivative is negative. Right? Because the change in the slope is negative, so that means that the derivative is negative. So if you find the slope by finding the derivative of the function, you find how the slope is changing by taking the derivative of that. So you have a concave down situation if the second derivative is negative, because that means your slope is constantly decreasing, right? So it's turning down the entire time. Conversely, concave up happens with a right side up parabola, where on one side you'd have a negative slope, right? Gets less and less negative, goes to zero, becomes positive, and becomes more and more positive. So therefore, you can call it f prime of x, but really it's the slope of the tangent. So the slope of the tangent is increasing, right? It goes from negative, starts pulling up, and it becomes more and more positive. So therefore, it's the slope of the tangent's derivative is going to be positive, which means that the derivative of the slope, the derivative of the derivative, is positive. So the second derivative is positive, means it's concave up, right? Up, positive is a good way to think about it. Down, negative is a good thing to remember it. And concavity is a lot of fun to say. Concavity. Get your concavity out of here. Here's a visualization if it helps. So here's a sine function. It's modified a little bit to make it clearer, but the green line is the tangent, and the orange dotted line is the slope thereof. So right now the tangent is horizontal, so zero slope. If we run this to here, this has a positive slope. The green tangent is a positive slope. It's going uphill, so therefore the orange line's up in the positive, right? If you run it to the other side, the slope's going downhill, so the tangent's going downhill, so the slope is going to be negative. And so you can see this transition happen, right? Where you say zero slope for the tangent, horizontal tangent, zero slope, negative slope, comes back, zero slope, goes to zero again, right? So that's probably not surprising to you, I hope not. But what I want us to see is this. Here, between here and here, we have a concave down situation. And as we roll through this, actually, so let's go from here to here. If you look at the orange line is constantly decreasing from here to here. I almost pointed at it with my finger, like you can see that. So if you watch the orange line, it's constantly decreasing until we get here. That whole spot is concave, and you can see it's a decreasing slope. The slope is going from positive on this side, getting smaller and smaller and smaller slope, zero slope, negative, 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 negative. And now, so that is indicative of a concave down part. And now our slope, the orange line, starts coming up because we get less and less and less negative, and you can see it rising. So as the orange line is rising, we have concave up. As the orange line is falling, we have concave down. As the orange line rises, concave up. As it falls, concave down, right? And so taking the second derivative shows us how the orange line is changing. And if you looked at just the second derivative, sorry if this is a little too many lines. Oh, that's a lot of lines. Let's run this backwards. So in this concave up format, right, you can see our slope is falling from here to here. And so you can see that the tangent of this purple dotted line, the tangent of this would be negative. So its second derivative would be negative. If that's too many lines for you, me too. And then concave up, you can see that the tangent is increasing during the concave up portion of the red line, right? From here to here, orange line's coming up, which means that the purple dotted line is going uphill, and its derivative would show you that it would show you that it's positive in that section, because all of the tangents on here would be pointing uphill. All right, maybe that's too many lines. Let's go back to this guy. So simple, cats. Points of inflection can show you curvature. So here's one way to think about it. This is a concave up. When your double derivative, your second derivative is positive, it's concave up because this was negative, gets less negative, gets less negative, gets more and more positive. So the derivative of the derivative of the slope, the change of the slope is positive here, right? Conversely, if you have a concave down, the slope is going from positive, less positive, 0, more and more negative. So this means the slope of the blue lines are decreasing. So when the slope of the blue lines are decreasing, you have a negative double derivative, you have a concave down. Great. Between those, when it stops being concave up and starts being concave down, or vice versa, you get it's called a point of inflection. It's when you could model part of it as up downward parabola and the other part as an upward parabola, and the point of the inflection is where they'd swap off, and you'd say, all right, well, it's no longer this one and it's starting to be that one, right? That's a point of inflection. Same sort of thing here. Even though this is kind of flat, you could model this as a parabola and this is a parabola, and then halfway through swap out, and that's your point of inflection. Okay, so this is just a little synopsis of concave up and concave down. Concave down means your slope is changing, getting more and more negative, so the second derivative is negative. In a concave up, your slope is getting more and more positive, so in concave up, your slope of that second derivative is positive because the change in the slope increases. All right. Inflection point is when you go from one system to the other. If you go from concave up to concave down, and they say that happens when the second derivative is 0. And I want to look at what that means with Desmos again. Okay, if you look from here to here, you can see that there's change in the slope, right? Let's run it backwards. The slope is constantly increasing from here to here. And also from here, well, it's concave down, the slope is changing. Right? You can see the slope falling. You can even make the sound effects. Right here, when you get this maximum slope, you can see that the slope doesn't really change much through there. And that's when it's going from concave up right here to concave down right there. You can see, I guess I can just drag this. You can see that right here there's a pause where the slope stops changing. The slope stops increasing and starts decreasing, right? It's going from a positive change to a negative change, and as it goes from positive change to negative change, it has to go through 0, right? Here's positive, positive, positive change, 0 change at this point, and then it's negative, negative, negative change, right? So concave up is positive, positive, positive change, point of inflection, negative, negative, negative change. Point of inflection, 0 change, right? Positive, positive, positive change, positive, positive, positive change. Oh, it starts slowing down and 0 change. So at these points of inflection where it trades off from being concave down to concave up, at those points of inflection, your double derivative, your second derivative, is 0 because it stops, it hovers. The slope doesn't change much there. It hovers, it goes through 0 and it stops. So that's why this is the case, because the change pauses from being positive, starts being negative, and at that point it has to go through 0. Super easy, so easy a caveman could do it. Or maybe that's just Mr. G after a long day. They talk about stationary inflection points versus non-stationary inflection points. Stationary just means that it's not moving, so its first derivative is 0. If it's non-stationary, its first derivative is not 0, meaning it's moving, right? So let's try that out. So they say, find and classify all the points on this. Okay, fine. Here's the function. Let's find the derivative. We can take the derivative. If you factor it, you get that. From that, we can say that its derivative is 0 at 0 and also at 3. So that's where these come from. I want to know when the slope is pointing downhill or pointing uphill. And first I'm just going to like throw this into a line diagram, and then we'll look at the graph and see what it looks like and connect the two. So just kind of follow me through the mathematics. I know that the first derivative is 0 at 0 and 3, because 0 and 3 can be put in here and you get to the 0 for the y. I'm going to just try some values on either side in between those. So let's try 1. Let's plug 1 into here, 1 into here. You get positive times a negative, so it should be negative here. Let's try -1 and throw it to see what happens here. If you put -1, this is still negative. This is positive, so it's negative on this side. And over here, if you put 4 in there, you'd get 4. This would be positive, this would be positive, so positive there. That means it's coming downhill, 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 downhill. Something happens here, but it's still going downhill. It just kind of like takes a break from going downhill and then keeps going downhill. And we'll look at that in a graphical sense in a second. And then at this point, it swaps and starts going uphill. So this is like physically which way is it pointed, down or up. If you take the second derivative, you take the second derivative of this, you get that, right? Do it from this mess, not this mess, because unless you love the chain rule, yes. I'd factor it again, and then this will, the second derivative will be 0 at 0 or 2. That's where this and this are from. Do the same thing, throw in values between there. So throw in 1, this will be negative times positive, so negative. Throw in -1, this will be negative times negative, so this will be positive. Throw in 3, so you get positive and positive, so positive. All right. Now they just like throw this at you. Oh, obviously concave up here, obviously concave down there, obviously concave up. Because they're looking at the second derivative and saying, hey, the second derivative is positive here, so the slope is slowly increasing the entire time, so it must be concave up. Here, concave down, the slope is decreasing each time, so it's got to be rounding down, concave down and concave up there, right? So they just write this part out. I want to take this, and on the next page I'll show you the graph. Peek. But if you're taking notes, they say stationary and non-stationary inflection points, and we'll look at that too. But so this is the line diagram, and this is the actual graph of the original function. This piece means from here to here means it's going downhill, and you can see that, right? All these slopes are pointing down, 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 down. It takes a break right there, and that's why you have a 0 at 0. Because it's not pointing down there, it's just pointing over, so it has 0 slope. But then it continues to point down, 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 down into the abyss. And then there's another 0 at 3, which is here. That's why it's 0 there. And then it starts pointing up. So then from here to here, it goes uphill, right? Uphill, 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 ad infinitum. Great, that's what this piece is about. It tells you like which way the slope is pointing. This part, the second derivative, tells you is the slope increasing or decreasing? Is it rounding up? Is it trying to round up, or is it trying to round down? And so from negative infinity, that way, sorry, it's backwards on my screen, up to 0, it's concave up, which means you could model it as an upwards parabola like that. Right? It's concave up because all those slopes are negative, but they're trying to get more positive, right? Because eventually here they're going to 0. So they're rounding up. From 0 to 2, from here to here, it's concave down, which means it could be modeled sort of like this, right? Where the slopes were at 0, and now they're getting more and more and more negative, going down, down, down. And at this point, they take a break. And they're like, all right, I'm sick of being negative. Let's change life up. And they start increasing. And that's at 2, they start increasing here. And you can see them start to pull up. They're starting to increase again. They're still negative, right? But now they're starting to pull up. They're still negative in here, but they're starting to pull up. And they get more and more and more positive as you go up. And so you can interpret this into this idea. You don't always have to draw them out, but it helps to make those connections. Cool. Here's a little visual aid, if you like. The stationary points happen when the single derivative is 0. It means that the slopes are 0 at that point. The non-stationary inflection points means that the slope is still pointing down or up. Here, these slope are pointing sideways. It's not moving up or down, not moving up or down. So those are stationary. Sometimes it's a turn, sometimes it's an inflection point. An inflection point is not a maximum or minimum, it's just when it goes from being concave up to concave down, right? And that happens here as well, goes from concave up to concave down. But it's not stationary, meaning that the derivative, the slope, is pointing up or down and not 0 at those points. It's a lot, but hopefully they make sense and you can sort of visualize what's happening. Cool? Looks good to me. We'll see you guys later.